Hello, and welcome to Empowered Learning. This video will be about a technique called integration by parts. We will talk about where this particular technique comes from, the order in which you should use it if you're having to perform integration. We'll talk about a strategy on how to properly pick or parse out your integrand so that you'll know what to select for the formula that we're going to use for integration by parts. And then we're going to go over several examples. So the first thing I want to tell you is that I'm assuming that if you are watching this video, that number one, you're familiar with derivatives. Number two, you're familiar with how to take the general antiderivative of a function. Number three, you have already learned how to use the substitution rule for differentiation. If you are not familiar with those things, I suggest that you watch my videos on those topics. If you just type in, hey, how to take derivatives, substitution rule for integration, antiderivatives, you'll see some of my videos pop up if you're on YouTube. If you are in one of my courses, then of course, all you have to do is look for the title in our virtual course area and you'll see the link for that. So with all those assumptions, I want to go ahead and say that with the substitution rule, we know that the substitution rule is essentially just the chain rule being undone, or the chain rule being done backwards. So the integration by parts is similar in that it is essentially the product rule being done backwards, or the product rule being undone. And so we're going to see how that looks so that we can come up with a formula for integration by parts. And then we'll talk about actually how to use it. So we see here that if I take the product of two functions and then I take the derivative of it, then the product rule just says the first times derivative of the second plus second function times derivative of the first. Then from there, if I was to integrate both sides with respect to x, then of course on the left side here, since we're undoing the derivative by fundamental theorem of calculus, that would just be whatever the integrand is. On the right side, we know that since we have two terms in our integrand on this side of the equation, we can split that up into two separate indefinite integrals. From that point, what we want to do is we want to solve for this particular term here, okay? And we'll see why in just a second. So to do that, what we need to do is we need to subtract both sides by this other term that we don't want over here. And if we do that, we'll see that we end up having the product of f and g minus this term is going to be equal to the term that we wanted to solve for. Now, if we assume that we let our function f of x equal u and our function g of x equal v, then we can rewrite this formula in the way that you see here. So of course we can let this be u. We're going to let this be dv since this is the derivative of our function g. Of course, this is u again here. This is v here. This is v here. And this will be du, meaning the derivative of u, which of course u is equal to f of x. So we see simply here, we just have this form of indefinite integral of u dv equals uv minus integral of v du. And I also have it here in prime notation form because for most of us, that is probably a more convenient way to express it. But you'll see me in this video go back and forth in between the two. All right, so now that we see that we know where integration by parts actually comes from, the next thing that we are going to do is to see how to use it before we get into some examples. So how do we select what is going to be u and what is going to be v? Okay, because again, we know that u is going to be f of x, v is going to be g of x. but in an integrand, how are we going to split it so that we know what's what? Well, simply put, we're going to let our function u, which we're also calling f of x, we're going to let that be the function that is easiest for you to take the derivative of, okay? And we're going to let v be the function, or dv, if I want to be more correct here, because we're going to be selecting based upon what we said here. We're actually going to be selecting what is u and what is the derivative of v. So we're going to select the function that is going to be easiest to take the antiderivative of so that we can find out what g is. Let that be the v prime or the dv. Okay, so that's essentially what we do. Now, in practice, sometimes it's not that easy to select what's going to be the u function, what is going to be the dv function. Other times it's very easy. Sometimes it doesn't matter which one you choose, it ends up working out the same way. And other times when you choose it one way, it works out real easy. The other way, it turns out to be a pain. Okay, so I'm saying all that to say that the only way you really get good at knowing what to pick and when is just to practice. Okay, but I'll try to do enough examples here to where you get a general idea of how to approach some of these basic problems. All right, so let's look at our first example here. So remember that we are going to try to take basically the most general antiderivative of this function, because in indefinite integral, that's what that means. And we look here and we know just by looking at this, we're not going to be able to take the antiderivative of it straight up, meaning just look at it and say, hey, the antiderivative is this. We also know, as far as the substitution rule is concerned, I could use the substitution rule. If I did it, let's just see what it'll look like. Here it would probably make sense to let u equal 2x, which means that my du is going to be 2 dx, and thus this means that 1/2 du is going to be equal to dx. If I did that, then I have a situation here where I would have e raised to the u, dx would be 1/2 du, and I would have to get very creative here and say, all right, well, if this is the case, x is going to be the same as u divided by 2, okay? And so from here, notice that if I do that, what I end up with is 1/4 on the outside, but I still have u raised to the u times e raised to the u du here. So what I've just done is made the problem that was a little more simple to do a lot harder, and I still haven't solved the problem of being able to look at something here and take the antiderivative of it straight up. So we know that using the substitution rule isn't going to work. Now, in the pecking order of things, we know that we start off trying to take the antiderivative straight up first. If we can't do that, then we do substitution rule. If we can't do that, then we do integration by parts. Okay, so we try those out. So in the pecking order, this is option number 3. And we see that options number 1 and 2 haven't worked. So therefore, we know we need to try to do integration by parts to try to do the integration for this particular problem. All right, so I'm going to erase this, and then we're actually going to go through the process of using integration by parts. All right, so when we use integration by parts here, remember that we want this to equal the indefinite integral of u dv. And so that means here I have to pick what is going to be my u, what is going to be my dv. Now, if we look here, we see that it's going to be real easy for me to take the derivative of x, okay? Matter of fact, it's actually going to be relatively easy for me to take the antiderivative of x as well, okay? So this x here could go either way. For the e raised to the 2x, we see here that taking the derivative and or the integral would be relatively easy as well, but I am going to have to use a chain rule to do it. This is one that's pretty well known. We know the antiderivative is e raised to the 2x divided by 2. So we will say that it can go either way as well. Okay. Now, what's going to be the deciding factor here is if I took successive derivatives, which one will terminate. Okay. And so here in this case, if I took the derivative of x, it's just going to be 1. If I took the derivative of 1, it's just going to be 0. If I took the derivative of if I took the antiderivative of e raised to the 2x, I would just keep on getting successive iterations of e raised to the 2x. If I took the derivative of it, I would get the same thing as well. Okay, so the fact that x, if I took successive derivatives, will terminate, I want to go ahead and use that for my u. And so I'm going to explain why that's important a little bit later here. Okay, so we're just going to let u equal x. We're going to let dv end up equaling e raised to the 2x dx. All right, so I'm not sure why my pen's not writing the way that it's supposed to. Okay, so now that we have that, our strategy here is we're going to figure out what du is by taking the derivative of x, and we're going to figure out what v is by taking the antiderivative or the integral of e raised to the 2x dx. Okay, so I'm going to rewrite this over here. And so if I took the derivative of x with respect to x, it will just be 1 dx, or just dx. If I took the antiderivative of e raised to the 2x, this would be e raised to the 2x divided by 2. And so we know that if I say the integral of u dv, according to our formula for integration by parts, we know this would be uv minus integral of v du. So using that formula here, I'm going to say integral of u dv, it's going to be uv times integral of v du. And our u is x, our v is 1/2 e to the 2x. So we'll just say this is 1/2 x e raised to the 2x minus integral of our v. If you noticed, our v here is just 1/2 integral of e raised to the 2x, and du is just dx. Okay. Now, if you noticed here, because we picked our u to be x, notice that the du here really was just a constant times dx. And so that was one of the reasons why we selected u to be x, because we knew that if we were to take the derivative of x, it would just be a constant. And by it being a constant, it makes it a whole lot easier to integrate what's going to be on the inside here. Okay. So now that we have that, we can look at this and say, yep, I know what the antiderivative of 1/2 e raised to the 2x is. I could do that relatively easy. Traditionally, we would use the substitution rule, but we know that this is one of those common ones where if we ignore the constant here, the antiderivative is just going to be like how I said here. It's e raised to the 2x divided by 2. Okay. So with that being said here, we know that the integral of x e raised to the 2x dx, that's the same as the integral of u dv. This is going to be 1/2 e raised to the 2x, and I forgot to write the x here, so I'm just going to write it there, minus 1/2 of integral of e raised to the 2x dx. And of course, the integral of e raised to 2x dx, all of that is just e raised to the 2x divided by 2. Okay? So I'm going to erase this. And we're just going to write that this is just 1/2 of integral of e raised to the 2x in its place. And then we'll add the plus c at the end because this is indeed an indefinite integral. So, aka the most general antiderivative. So if I rewrite everything, it's just going to be 1/2 x e raised to the 2x minus 1/4 e raised to the 2x plus c. And so that would be what the antiderivative of x times e raised to the 2x is by using integration by parts. Now, in showing you this, we're also going to learn another type of strategy for integration by parts, which is a bit quicker, and it's called a tabular integration. And so it's really used for two types of integrals. One is the one like what you're seeing here, where the integral, if we did it in succession, would terminate. And really what I'm saying here is that because we chose u to be x here, and if I keep on taking successive derivatives, I would eventually get to 0. If I had to do successive rounds of integration by parts to this particular integrand here, I would eventually get to where I would have to stop. Okay, so that's one type. The other type would be the kind where the integrals are going to be circular. And what that means is that when we choose our u and we choose our dv, both of those functions, the derivative of it is just going to be a variation of a theme on itself. So for instance, sine, we know that the derivative of sine is cosine. The derivative of cosine is minus sine. Derivative of minus sine is minus cosine. And you see, if we just keep on taking derivatives, we'll just keep on going in circles. Same thing with e raised to the, let's say, e raised to the x. We know that e raised to the x is a derivative of itself. E raised to the 2x, just like we looked at before, e raised to the 2x, the derivative of that is 2 times e raised to the 2x. The antiderivative of it is e raised to the 2x divided by 2. And every time we took a successive derivative of e raised to the 2x, we'll just be multiplying what we already have by 2. If we were to take the antiderivative of e raised to the 2x in succession, we would just be dividing by 2 every time we do it. And so when we have integrals that have those types of functions in them that are being multiplied times each other, they are great candidates for tabular integration because it basically helps cut down on the amount of work that we have to do to get what the final answer is going to be. Now, I'm saying all that because I'm now going to show you how to do this same problem by doing what we call tabular integration. And so I want to go ahead and introduce this now because depending upon the type of integral we're faced with, it may be more advantageous to do it this traditional way, or it may be advantageous for us to do it the tabular integration way. And I want you to be familiar with both ways so that you can use both tools when it is most efficient to do so. So what I'm going to do here is actually do one that is like this. I'm going to do x squared first so you can really see how this works. All right, so before I do this one though, I'm actually just going to do the one that we did first and then go into this one so you'll see how this actually works as well. So I'm just going to draw a little line here and let me change the colors right quick. And so let's do this one first. All right, so if we do tabular integration, we're going to do the same thing as we did before to start off with. We're going to select what our u is going to be, and we're going to select what our dv is going to be, okay? Just like how we did last time, we let x be u, but we're going to put it here in this column, and we're going to let e raised to the 2x dx, let that be dv, okay? Now, with tabular integration, what this is really used for is when we have to do more than one round of integration by parts. But I'm going to use it in this example to show you that we can, do it even though we don't have to do, successive rounds of it. In this column, what we want to do is continue to take successive derivatives until we get to 0. Okay, so here we know that the derivative of x is just 1. And we know that the derivative of any constant is 0, okay? And so by us getting to 0 here, this is what I mean by an integral to where if we do integration by parts, it terminates. The 0 here is basically telling us, hey, at some point, we're going to stop, okay? Now, we know that we need to take the antiderivative of e raised to the 2x dv. And if we do that, we know that we would just get 1/2 e raised to the 2x. If we did it again, we would get 1/4 e raised to the 2x. Okay. Now that we have that, how we actually perform the tabular integration in this case, since the derivative of u terminated as we did successive ones, we go diagonally across like this. And what we do here is we're going to put a plus, we're going to put a minus, okay? And so what we're going to figure out here is that the answer to this question is going to be this times this, which is going to be 1/2 x e raised to the 2x minus this times this. So this will be 1 times 1/4 e raised to the 2x. And then of course, since we're doing an indefinite integral, we do the plus c. Now what's happening here is that whenever we do the successive derivatives and successive antiderivatives, we're really following the same formula as the integration by parts formula. It's just that we're kind of doing it in abbreviated form here, okay? So now that we understand how this works, what we're going to do now is actually add on power here by 1. Instead of this being x raised to 1, we're going to let this be x raised to the 2. And then we're going to see how we could actually get this answer here. All right, so if we use tabular integration for this example, then we'll do u dv again, and we'll select x squared to be our u. We'll select e raised to the 2x dx to be our dv. If we do successive derivatives of, on x squared, we would have 2x, then 2, then 0. Because the derivative of x squared is 2x. The derivative of 2x is 2. Derivative of 2 is 0. Okay? Or any constant from that matter is 0. If we did successive antiderivatives here, then this would be 1/2 e raised to the 2x, and then 1/4 e raised to the 2x, and then 1/8 e raised to the 2x. Oh, and I just realized here that what this is, this was actually supposed to be for that. Yeah, because we saw that this answer was the same one as we had last time. So that's what this was for. And what I'm wanting to do now is actually show you what this is going to be. Yeah. So sorry if that confused you a bit there. Yeah, I wasn't supposed to have the squared on there. I was supposed to do it separately. All right, so again, we do the diagonals. We start off with plus and then just alternate signs, okay? And so I didn't mention this last time because it's not important for what we're doing now, but I'm going to go ahead and mention it because it'll be good for later. Notice that because this is 0 here, once we get to where we want to stop, of course you see how I'm doing diagonals across. At this point, we just go across here. And of course, I could put a minus there, and it's really not going to matter because 0 times anything is going to be 0. But this is going to be important to us whenever we face one of those types of integrals that I said was circular, meaning that what I choose for u and dv, both are not going to terminate, but it's going to be variation of a theme on themselves. And so being able to go across here when we see something similar to what we started with is going to be important. But I'm just going to, again, just draw this here to say, because this terminates, we go and look across, and that will let us know that that will be our last term, okay? Now, we've done this just like last time. We're just going to go across. So if we figure out what this is going to be, this is going to be x squared times 1/2 e raised to the 2x. So we'll just say 1/2 x squared e raised to the 2x. Pen is being delayed here. Let's try that again. Yep, still delaying. All right, and so next would be minus 2x times 1/4 e raised to the 2x. So that would be like 1/2 x e raised to the 2x. And then we'll have plus. And of course, 2 times 1/8 is going to give me 1/4. And then that'll be e raised to the 2x. And then, of course, the last term, when we look across, that's just going to be 0, okay? And, of course, ideally, we wouldn't want to write that. So I'm just going to erase it. And, of course, since this is an indefinite integral, we would do the plus c at the end, okay? And so this would be the answer to taking the integral of x squared e raised to the 2x. Okay. Now, traditionally, when we do integration by parts, what is shown is that we'll do integration by parts on something like this, and then we realize we got to do it again. And, you know, to me, it's just more efficient to do it this way. So that's why I'm coming out the gate and just showing you how to do it this way, because it really doesn't profit you a whole lot to be able to do successive integration by parts. When you can just do it via tabular integration, okay? All right, so let's go back and look at some more examples here. All right, so for our next example here, we see that we're asked to find out what is going to be the most general antiderivative of natural log of x squared, okay? So the first thing that we want to do to make life as easy as possible for ourselves is use our logarithm properties to rewrite natural log of x squared is just 2 times natural log of x, okay? And of course, if we do that, then we could rewrite our integral this way, okay? So now what we need to do is be able to choose what is going to be our u, what is going to be our dv, okay? So in this case, it turns out that the easiest thing to do here, and I'm going to switch colors here for a second, is if we let natural log of x be u, and I'm doing that because we know that the derivative of natural log of x is just 1 over x, so that's relatively easy. And if we take the antiderivative of dx, really 1 dx, if we take the antiderivative of any constant, it's just going to be that constant times x. And so the antiderivative of 1 dx is just going to be x. And so it's easy for us to take the antiderivative of 1 dx, easy for us to take the derivative of natural log of x. So because of that, we're going to make these choices here for our integration by parts. So we will say, let me switch this again. All right, let's go back to black here. All right, so therefore, we are going to say that the integral of, I wanted to put the 2 on the outside. All right, so 2 integral of natural log of x dx, which is going to be the same as 2 times integral of u dv, is going to be 2 times u v minus integral of v du. Okay. And here, if we know u is natural log of x, then du is going to be 1 over x. And if dv is equal to dx, then that means that v is just going to be equal to x. And so here, that lets us know that we're going to have 2 times, and then u and v, so it's going to be x times natural log of x minus integral of v, which is x, du, which is 1 over x, and this should be really 1 over x times dx here. Okay, and we know that because if I take the derivative of u with respect to x, that's just going to be 1 over x if u is natural log of x. And if we multiply both sides by dx, we end up getting this. So now that we have this, then this means that 2 times the integral of natural log of x dx is just going to be 2 times x times natural log of x. Of course, these x's here will just reduce to 1. So we just have 1 times dx. And of course, the antiderivative of 1 dx is just going to be x. So we'll have 2 times natural log of x minus x, and then all that plus c. And so what this ends up being here is that, and I'll go ahead and write this back in the original way that we had it. This means that the integral of natural log of x squared dx is just going to be 2x times natural log of x minus 2x plus c. Okay. And one of the things that we should glean from this, that will be very useful to us later, is the fact that we know that the antiderivative of natural log of x will just be x times natural log of x minus x. Okay. And so you'll see this at times in the future, especially if you are taking higher math courses. So this is a good one to remember. And if you can remember this, then you'll obviate the need to have to go through integration by parts to do it. But this would be the answer to this particular integral via integration by parts. All right, let's look at another example. All right, so for this example, we look and we want to see what's going to be our best selection for u and what is going to be our best selection for dv. Now, in looking at what we see here, of course, it's easy to take the derivative of r cubed, okay? It's also easy to take the derivative of natural log of r. We see, though, that, and we just got through seeing this, that taking the antiderivative of natural log of r is going to be a little bit harder than taking the antiderivative of r cubed. So because of that, what we want to do is we want to let natural log of r be what u is, because it's easy for us to take the derivative of that. And since it doesn't matter whether we take the derivative or antiderivative of r cubed, it's going to be relatively easy for us. We're going to let dv be r cubed dr. Okay. So now that we have that selection there, we know that this is just going to be equal to integral of u dv, which is the same as saying, let me erase that. It's the same as saying the integral of, uv times the integral of v du. Okay, and so now we're just going to plug in what we know. We know u is natural log of r. We know v, we would have to figure that out from this. So let's go ahead and figure out what that stuff is going to be here. So our du here will just be 1 over r dr. And of course, our v here will take the antiderivative of this. And that's just going to be r raised to the 4 divided by 4, or 1/4 r to the 4. So now that we have all that, we can come here, our u times our v. So it's going to be 1/4 r raised to the 4 natural log of r minus integral of v, which is 1/4 r raised to the 4. And then du is going to be 1 over r dr. Okay. So now that we have that in place here, we can see that taking the antiderivative of what we have here is going to be relatively simple, because of the fact that here this r and the r raised to the 4 will be a net r raised to the 3. And so now this would just be 1/4 r to the 4th times natural log of r minus 1/4. And then, of course, the antiderivative of r cubed is going to be r raised to the 4 divided by 4. And then we'll add the plus c at the end, because of the fact that we are taking an indefinite integral. And so our final answer here will be 1/4 r to the 4th natural log of r minus 1/16 r to the 4th plus c. And this will be our final answer. All right, let's move on to the next example. So for our next example here, notice that we have a definite integral, not an indefinite integral. So we know that by definition, this means that we need to find the area under the curve of this particular function. But in terms of integration by parts, what this means now is that we have to take our limits of integration into account. So here we're doing the integral of u dv. We would have to do that going from a to b now. And so our formula here would be u times v, and we evaluate that from a to b, minus integral a to b of v du. Okay, so that's how that's going to look different now. Now, for this problem, we can do this problem via regular integration by parts, or we can do it via tabular integration. And so since I want to get some practice in with the tabular integration. I'm going to go ahead and do it that way this time. Okay. So we'll have a column for u, have a column for dv, and since it's this t here, if we take successive derivatives of that, it will terminate. We want to allow that to be u. So we're going to let that be t, which means that we're going to have e raised to the negative t dt be our dv here. Now, in each column, we're going to take successive derivatives in the first column, successive antiderivatives in the second column. And then we're going to do that whole diagonal thing with the change of sign. And then whenever we get to 0, we're going to draw the arrow across to let us know that's where we stop. So here, the derivative of t is just 1. Derivative of 1 is just 0. The antiderivative of e raised to the negative t is just minus e raised to the negative t. And the antiderivative of that is going to be a positive e raised to the minus t. And how we're doing this, again, if you don't know, is we are using the substitution rule. And I'll just work that out real quick, just in case someone may be looking at this and are lost. So here, we know that we can't take the antiderivative of this straight up because we know that the antiderivative of e to the t is e to the t, but we don't have a rule for e to the minus t. So what we do is we'll let w equal minus t, which means dw is equal to minus dt. And so for here, we know that minus dw would be the same as dt. So if we did this now, this would be e raised to the w times minus dw. And of course, the antiderivative of e raised to the w is just e raised to the w. And then, of course, we have the minus there. And w was e raised to the minus t. So, again, I'm expecting that you're already familiar with the substitution rule. But just in case you kind of got lost here, this is how we know that the antiderivative of e to the minus t is negative e to the minus t. All right, so now that we understand how we're getting those successive derivatives here, we're going to go ahead and do our diagonals again. And of course, since we have a 0 here, we're going to come across. So it'll be plus, minus, plus in this case. And we know from what we see here, our first term is going to be t times a negative e to the negative t. So first term will end up looking like this. Minus, then we'll have 1 times e raised to the negative t. And then, of course, our last term here will be a 0, and we don't need to write that. And, of course, because of the fact that we have a definite integral here, we would actually have to take our result, and we're going to evaluate that entire thing from 0 to 1 by using the net change theorem from Calculus 1 or Calculus A. So now that we have that, we evaluate everything at 1, then turn around and evaluate everything at 0. So we plug in 1 everywhere where we see t. If we do that, then we'll have a minus e raised to the negative 1 minus e raised to the negative 1. And then we'll do the same thing with zeros. So if we plug in a 0 here, 0 times anything is going to give me 0 minus e raised to the negative 0 is just going to be e raised to the 0. And of course, from here, this would just be a negative 2 e raised to the 1. And here, if I do a negative times a negative, because we're ignoring the 0 there, negative times a negative is a positive, and e raised to the 0 is 1. So our result here will end up being a negative 2 e raised to the negative 1 plus 1. Or if you wanted to write it this way, 2 divided by e plus 1. All right, so at this point, we can go ahead and move forward to our next example. So for this next example, this will be a good example of what I call a circular integral. We know that this is a circular integral because if we look at e raised to the negative theta, we know if we keep on taking successive derivatives or successive integrals of e raised to the negative theta, it's just going to be a variation of a theme on itself. Same thing with cosine of 2 theta. Of course, the derivative of cosine is minus sine. Derivative of minus sine is minus cosine. And we know that we have the 2 theta that's inside the argument of that function. So by using the substitution rule, if we're taking derivatives, that just means we're going to have, we're going to multiply by 2 every time we take another derivative. If we're doing integrals, that means we're going to divide by 2 every time we do a successive antiderivative. So both of these functions act similar in that they are not going to terminate, but the derivatives are just going to be kind of circular in the sense that they're going to be variation of themes on themselves. Okay, so in this case, we are going to use tabular integration to help us quickly get to a point to where we're going to see what we started off with again, and then we're going to have to use some algebra to manipulate the equation that we get as a result to actually get our answer. Okay. All right. So let's first start with our selection of u and dv. Okay. So here we'll say u dv. So in this case, we will just let e raised to the minus theta. We'll let that be the u. And we'll let cosine of 2 theta d theta here be dv. Now for these, it really doesn't matter which one you let be u or let be dv, but I think it'll just be a little bit easier if I choose it this way. Okay. All right, so here, since we know that e raised to the negative theta, if we take successive derivatives of it, it is not going to terminate. What we are looking for is to keep on taking derivatives in this column and antiderivatives in this column to where we're going to see something with e raised to the negative theta times cosine of 2 theta again. Okay, so here I know that the derivative of e raised to the negative theta is just going to be minus e raised to the negative theta. The antiderivative of this is going to be 1/2 sine of 2 theta. Okay. If I do this again, the derivative of negative e raised to the negative theta is just going to be positive e raised to the negative theta. And if I take the antiderivative of 1/2 sine of 2 theta, that is going to be a negative 1/4 cosine of 2 theta. Okay. Now at this point, we can stop. And how we know we can stop is that if we do our diagonals again, we see that we got plus here, we got minus there, and notice that we have something that actually has a e raised to the negative theta in it and a cosine of 2 theta in it. So once we're at this point, we know we can stop. And how we're actually going to terminate is we are going to draw this across and do our plus sign, and that's going to let us know exactly where to stop. So if we use what we have here, then we're just going to say that this is equal to e raised to the negative theta times 1/2 sine of 2 theta that'll be our first term, minus, and so we got a minus times a negative, which is going to be positive, times another negative, which is going to be negative, so it'll remain negative here, e raised to the negative theta. And then we'll have times 1/4 cosine of 2 theta. And then for our last term, we're going to come across, and this is going to be plus a negative 1/4 e raised to the negative theta cosine of 2 theta. So now that we have this set up here, there is one last thing that we need to add here to make this complete. And so this is one of the reasons why the step here of knowing where to terminate is so important. In the other examples we've done, because our successive derivatives terminated to 0, we really could just say 0 times whatever it is going to be 0. And really what we should have been doing at that point is to do the integral of it, okay? And so I didn't put that in at that time because I didn't want things to get too complicated. But now you'll see that, yes, it does make sense to do that, okay? So remember that if we did successive integration by parts, this would just keep going and going and going and going, okay? But we also see that at this point, we saw across from here that we had this e raised to the negative theta times some number times cosine 2 theta, okay? So when we go across like this, this is the sign or the key to let us know that, hey, at this stage, what I need to do is I need to have an integral in this term here. And so since we normally factor out constants here, what I'm going to do is put an integration sign in there. I'm going to try to redraw that because that one was not that good. Okay, all right, let's see if I can hold this a little bit more steady now. Nope, that still didn't work. Let's try one more time. All right, yep, so that works. Okay, and so here, what you're going to find out is because we are terminating this circular integration here with this term, we're really not terminating, but we're saying that, hey, once I get to this point, I'm just going to start kind of spinning my wheels over again. So we're going to stop that, okay? And even if we did this the traditional way, we would just do integration by parts twice, and we would still end up with an equation like this. Now, at this point, what we notice here is that we have this term with a e raised to the negative theta cosine 2 theta, and I should have a d theta there on the end. Let me go ahead and write that. Yeah, because all of these, when I integrate them, should have d thetas there, but I haven't been writing it just for simplicity. So I have that, and I'll also have like term over here, okay? And again, it's because I'm ending this one with an integral, and this one has an integral in it. I'm going to add 1/4 times this integral to both sides, okay? And so when I do that, I'm going to come over here, and let's get back to this color. When I do that, I'm going to have 1/4 of this plus a whole of this. So 1 plus 1/4 of integral of e raised to the negative theta cosine of 2 theta. And again, I'm not sure why my pen is acting up today. Okay, so if I have that, then the rest of these terms, these two terms here, I'm just going to write as normal. So this will be 1/2 e raised to the negative theta sine of 2 theta. This will be minus 1/4 e raised to the negative theta cosine of 2 theta. Okay. And so now at this point, of course, we realize that 1 plus 1/4 is the same as 5/4. Okay. And so to solve for what it is that we want, which is the integral of e raised to the negative theta cosine of 2 theta d theta, we're going to have to multiply both sides of our equation here by the reciprocal of 5/4, which is 4/5. So if we do that, that means that integral of e raised to the negative theta cosine of 2 theta d theta would end up being 4/5 times all this business here. Okay. And of course, since this is an indefinite integral, at this point in time, I'm going to go ahead and do a plus c there. Okay. And so now all we have to do is we take the 4/5 and multiply it, distribute it to both terms here. And we said if we do that, 4 divided by 2 is 2. So this will just be 2/5 e raised to the negative theta sine of 2 theta. And if I take 4/5 multiplied by negative 1/4, that will give me a negative 1/5 e raised to the negative theta cosine of 2 theta. And then just plus c at the end. And we see that we now have what the most general antiderivative of e raised to the negative theta cosine of 2 theta d theta would be. Okay. And again, I know this seems a little long, but trust me, if we were actually doing it the traditional way of integration by parts, it would be a lot longer. Now, again, I want to reiterate that because of the fact that we knew that both of these functions that we chose for u and v were going to be circular integrals and circular derivatives, because we knew those, if we took successive integrals of derivatives, they wouldn't terminate. At some point, we had to figure out, all right, well, where are we going to stop? And we saw that at this particular point here, what we actually had was terms that we're actually going to see again. So we had e raised to the negative theta here, cosine of 2 theta d theta, and of course we had all that here. So we went down one more and said, all right, well, because we saw that we're going to stop here, we're going to do one more derivative, and we're going to let this actually be the step where we integrate, okay, or we put the integral sign back in there. And again, this is an augmentation of tabular integration to deal with these types of integrals here, okay? Now, I'm going to go back to a previous example here to show you why whenever we terminate, whenever we have a u that terminates, we can still use this particular scenario here, okay? So we're going to go back to that for just a second. All right, so if we go back to one of the examples that we started off doing here, we'll look at this one. I've erased this one, so we won't worry about this, but we'll look at this one. Notice here that I had this plus c here. So I'm going to get rid of that for a second and show you how we would actually come up with it. Of course, we can just put it at the end, but technically using what I just taught you, I'm going to show you why it actually makes sense to still have the plus c there. So if we were looking at this in the way that we did the problem with the circular integrals, remember we said that we're going to stop right here because we have 0, okay? And so let's say if we're going to now integrate wherever we stop, okay? If we do that, then of course we know 0 times anything is 0. So we're going to take the integral of 0 dx. And of course, we know that if the derivative of something is 0, that came from a constant. Okay, so we know that the most general antiderivative of 0 is just a constant. And so that is the reason why, in this case, I really didn't bother with it, because we know that for indefinite integrals, we have to put a plus c anyway. But if we were getting technical with the technique here, once we kind of go over and say, all right, we're going to stop at this particular term here, we know that this still ends up being some constant. And technically here, this would be not a plus, but a minus, because my signage here is minus. But it really doesn't matter whether it's minus or plus. We know that at the end of the day, because this is an indefinite integral, this is going to have to be this with some constant at the end. Okay, and we can just say, we can name it something else. We can say plus, a minus, a, where minus a is equal to c. Okay, so really doesn't matter. But again, I wanted to show you where this whole thing of doing the integral at the very end of this actually comes into play, and why it makes sense to do it whenever we have those circular integrals. All right, so let's look at some more examples. All right, so for our next example, we see that we have another definite integral, but this time we have some trig functions in the mix here. So we're going to see how we deal with this. Again, the very first thing that we want to do is make a selection of what is going to be our u and what's going to be our dv. Okay. So if we take a close look here, of course, x is going to be real easy for us to take the derivative of. Okay. Also, we know that if I keep on taking successive derivatives of this, I know that I'm going to be able to, terminate this particular derivative whenever I do successions of it. Okay. I'm going to do the traditional way of integration by parts this time, just because here the only time it's really worth it to do the tabular integration is whenever you have the circular integrals, or when you have something like x raised to a power or something that is 2 or higher. Okay, so here I'm just going to let x be u, and we're going to let cosecant square x dx, let that be our dv. Now, at first glance, we're like, don't know about that, because I really don't want to take the antiderivative of cosecant squared. But when you really think about it, knowing what the antiderivative of cosecant squared is actually easy, because we know that the derivative of cotangent is negative cosecant squared. So that means that the antiderivative of a positive cosecant squared is going to be negative cotangent. Okay, and just in case you forgot that, we can look at this as saying cotangent is cosine divided by sine, and if we take the derivative of that using the quotient rule says low function times derivative of high. So low function times derivative of high, so that would be minus sine, minus high function times derivative of low, and so derivative of sine is cosine, all that divided by the low function squared. And of course here, this SS means sine times sine, so that'll be sine squared, and of course c times c is cosine squared, so this is like 1 sine squared plus cosine squared, and we all know that sine squared plus cosine squared is 1, and thus 1 divided by sine squared is going to be cosecant squared. And of course I've been carrying those negatives there. So we know that it's relatively easy for us to take the antiderivative of cosecant squared. Okay, so now that we know that, we can go ahead and use our integration by parts formula after we find out what our du and our v is going to be, and just move forward and evaluate the definite integral at that point. All right, so we know that if u is equal to x, then it means that du here is going to be equal to 1 times dx, or just dx. We also know that if dv is going to be secant squared x dx, then that means that v is going to be minus cotangent of x. And so with this being our u and all this being our dv, that means the integral of u dv. Let's try to make that look a little better. Pen is having a mind of its own today. All right, so the integral of u dv ends up being uv minus integral of v du, okay? Now, notice that we have definite integrals here, so we're actually going to have to include the fact that this u times v needs to be evaluated from pi over 4 to pi over 2, and same deal here, okay? So we're going to erase this and make sure that we include the fact that we're actually evaluating a definite integral here. So I'm going to do uv and evaluate that from pi over 2 to pi over 4 minus integral pi over 2, pi over 4 to pi over 2. Got that backwards. Let's try that again. Okay, pi over 4 to pi over 2. This is pi over 2 here. And this is pi over 4. Okay. And this is going to be v du. And of course, u is x. V is minus cotangent x. And we evaluate that from pi over 2, from pi over 4 to pi over 2. I don't know why I want to write pi over 2 first. All right, so pi over 4 to pi over 2. And then minus integral of pi over 4. I did it this time. Pi over 2. And then v is going to be a minus cotangent x, and then du is just going to be dx. Okay. So now that we have that, let's go and work a little more on this now. So here I'm going to go ahead and evaluate what this is going to be. So we'll say minus pi over 2 cotangent of pi over 2 minus pi over 4 cotangent of pi over 4. And then from there, we'll have this minus and minus will give us a plus. And so here we need to be able to evaluate the antiderivative of cotangent. And if I remember correctly, that's going to be natural log absolute value of sine, maybe minus, but I'm going to do it via substitution rule just to double check myself there. So here, what I'm going to do is, let's do this pi over 4, pi over 2, and I'm going to write this as cosine of x over sine of x dx. And so at this point, I'm going to change colors here. Let's use this. We're going to let u equal sine of x. So I'm using substitution rule here. Then, let's try this again. Then we know that du is going to be cosine of x dx. Okay, so we know that all of what we have up here is going to be du dx. So all of this is going to be du, sorry. And what this is going to be is just u. And so now what we would need to do, of course, is figure out what u of pi over 4 is, which that's going to be the same as sine of pi over 4, which is going to be 1 over square root of 2. Or some of you may like to rationalize your denominator and write it as root 2 over 2. And u of pi over 2, so sine of pi over 2 at 90 degrees is just 1. And so here, this would just be 1, and this would just be 1 over root 2. Okay. So now that we have all of that, let's go ahead and also work on what we have here. So move down some here. So therefore, u dv, and I'm going to do this in a different color too. So we know cotangent of pi over 2 is just cosine of pi over 2 over sine of pi over 2. And here, cosine of pi over 2 is just 0. So it doesn't really matter what this is, but we know sine of pi over 2 is just 1. So all of this just ends up being 0. Okay. If we do the same thing, cotangent of pi over 4, that's going to be 1. And that's because of the fact that cosine of pi over 4 and sine of pi over 4 equal to the same exact thing. Yeah, it's not writing the way I want. So let's try to make it do that. And of course, both of these, 1 divided by root 2, 1 divided by root 2, so you end up getting 1. So what we have here is just 1. So now that we have all that, we can go ahead and finish up working this problem here. So we have a negative pi over 2 times 0, so we can just ignore that term. We have a minus times a minus, which is a plus. 1 times pi over 4, so all this just ends up being pi over 4. And then we have plus. Our new integral now is going to be from 1 divided by root 2 to 1 of du over u. And we're going to make that du look a little better here. Wow. All right, du over u. And so now we know that the antiderivative of 1 over u du is just going to be natural log of absolute value of u. So this is natural log of absolute value of u. And we're going to evaluate that from 1 over root 2 to 1. So we have pi over 4 here, plus, when we evaluate it at 1, absolute value, natural log absolute value of 1, minus, and then we'll see natural log of 1 divided by root 2. Okay. And we are almost done here. So we know that natural log of 1 is just 0. So the only thing we have to worry about now is the natural log of 1 divided by root 2. But of course, this can be written as natural log of absolute value of 1 minus natural log of absolute value of root 2. Okay. And that's going to be that with the minus on it if we take care of all of that. And again, natural log of absolute value of 1 is just 0. So all we really have here is natural log of absolute value of square root of 2. So from here, all of that just ends up being pi over 4 plus natural log of square root of 2. And we don't need the absolute value signs because square root of a number that is non-negative will always end up being positive. And so at this point, this is the answer. But if we wanted to get fancy, since square root of 2 is 2 raised to the 1/2, we could also rewrite this answer this way if we like. Okay, so this answer or this answer is acceptable. All right, let's move on to the next example. All right, so for our next example here, we actually see that we have something that's kind of similar to what we've seen before, meaning that we have to take the integral of a natural log function. One thing that we want to note here is that since we have natural log of square root of x, that we could rewrite this integral as, and this is because of the fact that we could rewrite natural log as natural log of square root of x as natural log of x raised to the 1/2. And of course, that could be rewritten this way. We know that this integral could be rewritten as the integral from 1 to 4 of 1/2 times natural log of x dx. And so in knowing that, we could rewrite this integral this way. And if you remember what we did back on a couple of examples ago, I think it was like the second example that we did, we actually found out that the antiderivative of natural log of x is just going to be x times natural log of x minus x. And remember, we found that out by doing integration by parts. And so since we see this, we're not going to recreate the wheel again. We're going to use what it is that we already know. And so we're going to use the net change theorem from Cal A and evaluate the antiderivative of natural log of x, which is just x times natural log of x minus x, from 1 to 4. Okay. And I'll come down here and do that. So we'll have 1/2, and then we'll plug in 4 everywhere where we see x. And then after that, we'll plug in 1 everywhere where we see x. Okay. And of course, we know that natural log of 1 here is going to be 0. Oh, let me not do it in that color. That's a little too bright. Let's do it in red. So we know natural log of 1 is 0. And of course, 0 times 1 is 0, and 0 minus 1 is -1. But we have a negative times a negative here, which is going to end up being a positive. So when we move down, write this again, we know this is going to be a +1 here. Now over here, we could choose to leave this as natural log of 4 times 4 minus 4, or we can go ahead and multiply that 1/2 through. What I'm going to do here is just write this down as is for this step. And then from here, we will go ahead and just multiply the 1/2 through to all those terms. So before I do that though, I'm going to go ahead and simplify this to -3 and then multiply on through. So this will be 2 times natural log of 4 minus 3 over 2. And of course, this is 2 times natural log of 4. We can put the 2 up in the exponent here. That'll be natural log of 4 squared, or natural log of 16 minus 3 over 2. So this will be a simplified version of our final answer. Of course, 2 times natural log of 4 minus 3/2 is acceptable too. I personally just like to condense down the logarithms as much as I can, just because of the fact that if you're actually going to use that expression in the calculator to figure out what the actual number is, natural log of 16 is a little easier to type than 2 times natural log of 4. All right, let's move on to the next example. All right, so for our next example here, we have another definite integral, but this time we're asked to find out what the integral is going to be, where the integrand is a product of 2 functions that end up having those circular integrals like what I was talking about before. Okay. Now we see here that s is the variable and t is a constant, so we have to make sure we remember that when we do our integration or take derivatives or whatnot. But in this case, we're going to use tabular integration to do this because of the fact that we do have this circular type integration going on here. So what we're going to do is make our columns for u and dv. I'm going to say let e raised to the s be u, and sine of constant value t minus s ds, let that be our dv. Okay. And so what we're going to do again is take successive derivatives of column u and successive antiderivatives of column dv until we see something diagonally across that says e raised to the s times sine of t minus s again. Okay. So we know that the derivative of e to the s with respect to s is just going to be itself. So that's easy. If we take the derivative, the antiderivative of sine, that's going to be a minus cosine. And then of course from here, we need to take whatever the derivative of t minus s is going to be. And remember, and this is because of the substitution rule, t is a constant, so the derivative of t is 0. And of course, the derivative of minus s is just going to be a minus 1. So if I took minus 1 and divided it by this, a minus divided by a minus is going to give me a plus. And since we're going to do this again, we're going to put another ds here since we're going to take the antiderivative again. All right, so next row, the derivative of e to the s is e to the s. And here again, if we take the antiderivative of cosine, that is going to be sine. And again, the derivative of t minus s is going to be just a minus 1. So we're going to put a minus here and then put the ds again. All right, so notice here that I'm only putting the ds's here for formality because we're doing tabular integration and this is going to end up being successive. The only ds that I'm actually going to really need is this last one here. So I'm just going to erase these other two because I don't want to complicate things. So we're going to go ahead and do our diagonals here. And we know at this point, since we see e raised to the s, sine of t minus s in here, we know that we'll stop. And so we'll use this particular term to integrate and stop. In other words, this last term here will actually have an integral sign in it. And of course, since it's a definite integral, it'll end up being the integral from 0 to t. So looking at this, we know now that integral of 0 to t of e to the s times sine of t minus s ds. All of this is just going to equal, and I'm going to hold off a minute on how I actually write this as far as the definite integral part of it. I'll wait to the very end to kind of put all of that together. So here I'm just going to say e to the s times cosine of t minus s. It's going to be e to the s times cosine of t minus s, like this. And then minus. So we have minus a minus, which is going to be plus e raised to the s sine of t minus s. Yeah, pen is starting to drag again. And so for these first two terms here, since we're not going to have an integration sign on it, what we want to do is write it like this, meaning that we've already gotten what the antiderivative of those terms are. Well, these terms are antiderivatives, and so we just need to evaluate them from 0 to t. Now, for this last term, since we're going to terminate the amount of terms that we write with this last one here, of course, we have plus here, but we got plus a minus, so it's going to be minus here, integral from 0 to t, and it's going to be e raised to the s times sine of t minus s ds. Okay. And so now that we have that, then of course here what we see is I can take this term and I can add it to both sides. So if I add this to both sides, I'm going to have a positive one of these plus another positive one of these, which is just going to be 2 of these. Okay. And so, of course, from here, what I have left is I have this antiderivative, but of course I got to evaluate from 0 to t. And so I'm going to go ahead and take care of that now. And I'm going to plug in t everywhere where I see s. So it's going to be e to the t cosine of t minus t plus e raised to the t sine of t minus t. So that'll be the first term. Not first term, but these will be the first terms. And now we'll do the same thing again with 0. So I'll have e raised to the 0 cosine of t minus 0, which is just cosine of t, plus e raised to the 0, and it'll be sine of t minus 0, which is just t. And again, we know that e raised to the 0 here is just 1. And here we know that t minus t is 0, and cosine of 0 is 1. Sine of 0 is 0, which makes all that 0. Okay. And so I'm running out of room here, but what we can see from this is I have an e raised to the t out of all this, and then I have a minus cosine of t minus sine of t here. And so I'm going to actually write this up here now. So here we know that our final answer is just going to be just this integral here, so we'll need to be able to divide by 2. So I'm going to take all of this and divide it by 2 as well. I'm actually going to come up here and write the final answer. And so here, integral from 0 to t of e to the s sine of t minus s ds. Here, that is just going to equal here, and this will be 1/2, and then in this first term here, e raised to the t, and then we have a minus cosine of t, and if we distribute that minus to the second term, it'll be a minus sine of t as well. And that would be our final answer. Of course, if you want, you could factor out the a -1 out of each term. Not necessary that you do this, but just depending upon if you want the answer to look a different way here. If you factor out the negative, then it will look like that. Either way, answer is fine. All right, so let's move on to our next example here. And so we see that for this example, we're kind of being asked to use the substitution rule first before we actually apply integration by parts, because it may make life a little easier for us. So we will go ahead and do that. So if we're going to do that, then let's let u equal x cubed, because that's the innermost function here. So we let u equal x cubed, then that means du is going to be 3x squared dx. And matter of fact, let's not make this u, let's make this w. Just because whenever we do integration by parts, we'll be using u for that. And here, this means that dw over x squared is actually going to be equal to dx here, okay? So if we go and substitute what we need to here, we'll have x raised to the 5 times cosine of w, and in place of dx, we're going to have dw. Let me draw that again here. So I'm going to have dw over 3x squared. Okay. And notice here that the x to the 5th over 1 here, and the x squared down here gives us a net x cubed in the numerator times cosine of w dw, and of course we have an extra 1/3 because 3 is in the denominator here. I'll just write it like that for now. And here we'll go ahead and factor out the 1/3. And remember here that x cubed, we don't want this here, but remember that x cubed is indeed w. So we could replace that with w times cosine of w dw. And so we see by using the substitution rule, we still have to do integration by parts, but we're only going to have to do it once because we have it in this form. And because of that, now we can go ahead and apply integration by parts. And let's switch colors here. And we're going to let w be u here. And we're going to let cosine of w dw, let that be dv. Okay. And because of that, then that means that du is going to be dw, because derivative of w with respect to w is just 1, so there's 1 dw. And v here, we know that the antiderivative of cosine of w is going to be sine of w. Okay. So now that we have all of that, then we know that this is just going to be 1/3 integral, well, sorry, let me back up here. 1/3, and of course, I'm going to write the formula in here, uv minus integral of v du. And our u is w, our v is sine of w, minus integral, our v again is sine of w, and our du is going to be dw. Let's try to make that look a little better. Okay, and of course, since we're doing an indefinite integral here, all of this is going to be with a plus c at the end. Okay. All right, so therefore, x to the 5th cosine of x cubed dx, because that's what it is that we're trying to solve here. It's just going to be 1/3 times. I'll leave everything in w until we're actually done doing our integration here. So we see here that the antiderivative of sine is going to be a minus cosine, but a minus cosine times -1 gives us a positive cosine w, and all that plus c. And so from there, we'll now go and substitute back x cubed where we see w. So that'll be x cubed sine of x cubed plus cosine of x cubed, all that plus c. And let's make that x look a little better. And we see that that ends up being the answer that we need to get. And so because we use the substitution rule first, that actually made using integration by parts relatively simple here to use and employ so that we can get our final answer. And so this is an example of how we can actually use the substitution rule. We've been using it a lot actually, but in a more traditional sense, using the substitution rule first and then using that to be able to perform integration by parts on the integral of some function. Okay, so for our last example, we're going to do something a little different here, and we're actually going to look at this formula for the nth antiderivative of sine. In other words, sine raised to the n power. We're going to take the antiderivative of that. That's probably a better way to say that. So, and we see that it's this formula here, and what we want to do is prove that formula is actually that, and then we want to use it to figure out what sines, the antiderivative of sine squared x is, and what the antiderivative of sine raised to the 4th x is. Okay. So to start this, notice that we are going to be using integration by parts here. So this integral here is going to be integral of all of this is going to be u times dv. Okay, and what we're going to have here may very well end up being, well, it actually is going to be uv times integral of v du. Okay, so it's going to look something like that. I notice here that for this first term, I have a sine raised to the n minus 1, and I have cosine here. Okay, so what that's telling me is that either sine raised to the n minus 1 of x is going to either be u or v here. Okay, since I have to choose between u and dv, that kind of gives me a hint here to let u equals sine raised to the n minus 1 of x, which is the same as saying sine of x raised to the n minus 1. And if we do that, then it means that dv is just going to be sine of x dx. And again, if I multiply sine of x by sine of x raised to the n minus 1, the exponents add here, because it's like sine of x raised to the 1. Those exponents add to go back to just sine raised to the n. So that works out. So from here, what we'll do is just set up our integration by parts and kind of see where it takes us. Okay. So here we'll say integral of u dv, which you know is the same as saying integral of sine raised to the n of x here. It's just going to be uv minus integral of v du. And our u here, again, is just going to be sine of x raised to the n minus 1. And I'm going to write it like that until we don't have to use it anymore. Our v, of course, we haven't figured that out yet. But if dv is sine x dx, then it means that the antiderivative of sine is going to be minus cosine. Okay, so our v here is going to be a minus, I'll do a minus cosine of x. And this will be minus integral of our v again, which is minus cosine of x. And now du, I'm going to write that in a different color here. So let's see, I'll do it in black. So if u is this, then du is going to be n minus 1, using the chain rule here, n minus 1 times sine of x raised to the n minus 2. And then, of course, if we take the derivative of the inside function sine x, that is going to be cosine of x. And then dx. So all that's got to fit in here. So I'm going to have to make a little room to make that work here. Or what I'll just do, I'll just cheat. And we'll just do this. Say all of that goes here. Okay, and then I'll just write it all out in the next step. All right, so therefore, it's integral of u dv. What we end up having here again is this minus sine of x raised to the n minus 1. And this will be that times cosine of x. And then this will be plus cosine of x times, and now we got to write all this stuff in. N minus 1 sine of x raised to the n minus 2 times cosine of x dx. And so if we notice here, we know that cosine and cosine multiply to be cosine squared. So I'm going to go ahead and simplify that. We also see that n minus 1 is a constant. So we're going to pull that n minus 1 on the outside. So here I'm going to rearrange this to where I have cosine squared x here. get rid of that there. And we'll have n minus 1 like this. And then we'll do the integral. And of course, all this business here would go with the integral. All right. Now, the next thing that we see here is that cosine squared is not going to do us much good to leave this as it is. But we do know that cosine squared is 1 minus sine squared. Okay? And in doing it that way, that will force us to have a sine of x raised to the n minus 2 term, like what we need here. So what I'm going to do next here is just going to rewrite this totally, and I'll just go ahead and drop to the next line to do that. So here we'll keep all the rest of this the same. X raised to the n minus 1. Seems like my pen is just getting worse and worse. All right, let's try one more time. X raised to the n minus 1. All right, and then we got n minus 1 here. Integral, and instead of writing cosine squared, we're going to write 1 minus sine squared. And we'll multiply that times sine of x raised to the n minus 2 dx. Okay. All right, so now that we have that in place here, we see that we can take this and distribute it to both terms. And of course, we'll have that sine of x raised to the n minus 2 dx like we want, but we're also going to have another term that's just going to be sine squared times sine x raised to the n minus 2, which is just going to leave us with sine of x raised to the n. Okay, and we want that as well because remember, that is what this actually is. Okay, that's what we started off with. Okay, so we don't want to forget that. So here, since we don't want to forget it, I'm going to go ahead and write it in here. That this is going to be sine of x raised to the nth power and here, of course, need to rewrite all the rest of this stuff. Cosine of x plus n minus 1. And here we're going to have two separate terms here. So this would be n minus 1 with the sine. Oh, let me not write it like that. All right, so sine of n minus 2 of x, I'm going to write it like this for now. And this is also going to be minus n minus 1. And of course, sine squared times sine of n minus 2 squared is just going to be sine raised to the n. Okay. And so if we look here, we'll see that this term and this term are like terms. So what we could do is add this term to both sides. And if we do that, we're going to have 1 plus n minus 1. And of course, 1 plus n minus 1, that just equals n. So on the left side here, this will just simply be n times sine raised to the n of x dx. That is going to equal everything else that we have here, which is going to be minus sine of x n minus 1 times cosine of x plus n minus 1 sine raised to the n minus 2 of x dx. Okay. And so finally, we see here that in order to get sine raised to the n of x dx, the integral of that by itself, we would have to divide both sides by n here. Okay. And if we divide both sides by n, then of course this goes away, and we would have over here both terms here being divided by n. So I could just come here and just divide this by n and divide that by n, and that will take care of both of those terms. And if we come back up here, we'll see that that's kind of what happens here. The 1 divided by n that is there would be understood 1 divided by n here. And of course, the n minus 1 divided by n, that is what we see here. And everything works out. So now that we have a way of expressing the antiderivative of sine raised to the n of x dx, then of course we could use this formula to be able to figure out what sine squared, the antiderivative of sine squared would be, the antiderivative of sine raised to the 4th. And so instead of trying to write that all out, I already have that worked out, so I'm just going to show you what it looks like. And then we'll go ahead and end this video here. So let me just show you what that looks like when we work it out. So if we use that formula to figure out what sine squared of x dx is going to be when we take the most general antiderivative of it, of course we use that same formula here, and you see that we'll get minus 1/2 sine x cosine x, and then of course this is the n minus 1 over n part, and this just ends up being another 1/2. Of course, the sine raised to the n minus 2 power, since n is 2, because since that's what n is here, then of course this ends up being just some constant, and of course the antiderivative of a constant is just going to be a linear term there, and so that's how we get the 1/2 x there, and that ends that. And so of course here this is actually an acceptable answer, but we do realize here that sine x times cosine x here is the same as 1/2 of sine of 2x, so we can write that in a more condensed form here. And so we see that if we replace sine x cosine x with 1/2 of sine of 2x, then we just get negative 1/4 sine of 2x plus 1/2 sine x plus c. Okay. Now, we see that if we use sine raised to the 4th, we have a little bit more work to do because we have to use this formula twice. So here we see that since n is 4, of course 1 over n sine raised to the n minus 1 cosine of x, and then of course n minus 1 over n times sine of n minus 2. Notice here that all this on the outside works out fine, but here we have the integral of sine squared, and of course what we just found out there, we would just go ahead and substitute that in to keep from having to recreate the wheel. And then, of course, from there, the rest of this is just us trying to do what we can to simplify this, to make this look as nice as possible. Okay. And of course, I break up this sine of x raised to the 3 and into sine squared times sine. Of course, for the fact of sine x times cosine x is 1/2 sine of 2x. And then here we also realize that sine squared is going to be sine squared of x is going to be 1/2 of 1 minus cosine of 2x. That's one of your trig reduction formulas. And so if we use all that information here, of course, we'll substitute in 1/2 times 1 minus cosine of 2x here. See all that substituted in. And then from there, it's just a bunch of arithmetic to try to get it down to something that looks, relatively simple. So, and of course, we get to this final answer here. All right, so I know this was a long video, but I had a lot of examples, and I wanted to make sure that I showed you a lot of examples because integration by parts is very important. For those of you that will be taking higher math courses, or you will be using this in the future, you're going to see integration by parts a lot. So, and again, that's one of the reasons why I wanted to make a lot of examples so that you don't get thrown off based upon some examples that you see. I had a lot of easy ones, some that were a little bit more tough, a little bit interesting, but I think with this, you will have enough to be able to at least have a foundation in how to do integration by parts. And I really hope this helps in your understanding. Take care.